Okay, for our final talk today, I'd like to call Jonathan.
Hello, everybody. Uh, my work here in QTNano is in between the quantum chemistry and the machine learning techniques, and I work with both sides. And in this case, I will present my work about the framework we develop with employee correlation analysis and a feature engineering process, which basically aims to get to make it very easy to take insights from quantum chemistry data. Uh, I have worked with both sides, and not just in this work, and soon we will have a postdoc, João Paulo, that arrived in March to work with me in between these two fields. So the motivation of this work is basically that we arrive in the fourth paradigm, which basically means that now we have a large amount of data, and we cannot handle this manually. We cannot look at each calculations and see each property and so on. So based on that, the quantum chemistry studies that we have developed the current frequently have some problems. For instance, the insights are based on the most stable structures that normally are a very few quantity in relation to the all the calculations performed. For instance, in a study you calculate a lot of calculations, and then you look at the most stable structures to see some property or something like that, and all the other calculations you don't employ, but there is information there. Uh, uh, there is also a lot of visual description of the molecules. For instance, oh, the most stable structures seems to present several oxygens on the surface, something like that. But it's a very personal way to look to the data. You are putting your personal view into the results you are looking for, and also in your conclusions. So it's a problem. Uh, and also visual identification of trends. For instance, you look to a graphic, you say, oh, there is a ascendance relationship in the data or not, but it's a very personal, you don't employ analysis to do that. To address this kind of problems, we propose a solution based on employee correlation analysis, with are very interesting because it can handle a large amount of data. It's a very well-defined methodology, so it reproduces, and you can have statistical information of your uh, correlations and things like that. It's calculated and it's implemented. And the challenge in this part is not calculate the correlation itself, but in do a good filterization process. And I will address this in a moment. Just now, I would like to address the correlation analysis, which is basically a coefficient you can calculate based in pair rate data. So you have a pair of x and y values. You have several data based on that. You can calculate a coefficient, which lie between minus 1 and 1. It basically seems the sign can be positive or negative. A positive sign means that when x increase, y increase together, which is a ascendant relationship. The opposite, if the sign is negative, you expect that when you increase x, your y decrease. And how much expected, it's exactly the same of how strong is the correlation, which is as large as R. For instance, in this case, in most of the cases when you increase X, Y increase together, but in this case, it's not so frequent. In our case, we don't employ the Pearson correlation, which is the standard one. We employ the Spearman correlation because it employs ranked data and it's more robust against are more robust to outliers. So we have we know how to calculate it, but we need the data itself. And when you calculate a atomistic simulation, we have basically two types of data. You have, for instance, molecular information, for instance, energy and HOMO levels. For each molecule, you have a value, for instance. You calculate several clusters. For each molecule, you have energy and HOMO level. And then this is a pair data you can put in a graph and calculate the correlation. There is another kind of information, which is the atomic information, which for each atom in the system, you have a value in this for this vector here, and you cannot put this in a graph or calculate the correlation. So the filterization process here aims to take atomic information, for instance, the charges in a system, and somehow take this information and create molecular information based on that. And then when we take, for instance, some kind of molecular information based on the atomic charges, we can calculate the correlations. So to do that, we developed this this structured this approach to transform atomic information into molecular information, which basically take a bag, which is a set of information of the atoms, and a class, for instance, the effective coordination number of the atoms, and a class of the platinum atoms of the system, for instance. You take these two guys together and select the data. So now you have the platinum atoms effective coordination numbers, and then you apply an operator, for instance, the average, and in the end you have the average of the effective coordination number of the platinum atoms of your systems, which is a molecular data, and with that you can calculate the correlations. It seems simple, however, you can look to several levels of deepness in this way. For instance, you can look at the effective coordination number of the atoms in the systems, for instance, the cerium atoms. You can also look to the effective coordination number of the cerium atoms in the surface, or even to the effective coordination number of the cerium atoms in the surface with effective coordination number around 5. So you can increase the level of the amount of information as much as you want. Of course, you need if you would like to look very deep in your data, you need a lot of data. But based on that, you can basically generate a large amount of molecular data, and with that, calculate the correlations. So with this framework, we address 3 quantum chemistry datasets that were developed here in our group. Mixed oxide nanoclusters that was studied by Priscilla. Platinum-based alloys that was developed with Paulo. And methane dehydrogenated candidates over transition metal was developed by Carl. Basically, they have your importance, but the focus here is the correlation analysis. And if you have some doubt about this data set, you can talk with my collaborators. Here is some example of data sets of the results. Sorry. In each column, I have a system. For instance, the mixed oxide here, it's rich in zircon atoms, and here is rich in cerium atoms. In each cell, in each row, I have a different filter. For instance, here is the number of cerium atoms exposed to the vacuum, the number of zirconium atoms exposed to the vacuum, the number of oxygen atoms exposed to the vacuum, and so on. The vertical axis are the values of this filter, and in the horizontal axis, there is the relative energy. In this case, we would like to know which filter have influence over the stability. So we are looking to the relative energy of the clusters. Then what we can see, for instance, is that the zirconium atom, the number of zirconium atoms exposed to the vacuum, have a very large correlation and ascendant with the relative energy. What it means? Basically that the zirconium atoms would like to reduce the cluster, the more stable clusters present a few number of zirconium atoms exposed to the vacuum, which means that the zirconium atoms would like to stay in the core. But it's also observed for the cerium atoms. Then we have to look to the difference of the magnitude of the strands. And in the case, the magnitude of the strands of the zirconium atoms are stronger. So based on that, we can understand and interpret that the zirconium atoms have a higher preference to stay in the core in relation to the cerium atoms. And based on this type of interpretation of the correlation analysis, we can get insights from the data and so on. We have, for instance, other insights we get from the data. For instance, a difference in the coordination of the oxygen atoms, which are in this kind of mixed cluster, are different from the surface, for instance. We published this article in the last year. The second work was based on platinum-based alloys, and we studied it with several transition metals. For instance, here I show different alloys per column. So in this first column, there is the alloys between platinum and iron, and in the last column, between platinum and silver. I reduced the size because there is much data to show. In this case, for instance, the number of atoms in the surface seems not to be a very important feature, which is strange because if you have a cluster with a large amount of atoms in the surface, you would expect that it's not very stable. However, in this case, the most important feature are the type of atom in the surface. For instance, some clusters prefer to have a lot of platinum atoms in the surface, while other alloys prefer to have a few amount of platinum atoms in the surface and instead have transition metal, the other transition metal in the surface. So based on that, we develop, in this case, a toy model to explain, to present the insights we have from the correlation analysis, and we explain these correlations based on the difference of the radius between the platinum atom and the transition metal in the alloy. In this case, the difference was explained based on the difference of the radius of the platinum and transition metal and the surface energy. And with that, we can predict which atom will stay in the core or in the surface. In our last work, was quite more difficult to address this kind of systems. Basically because different from the alloys, when you have several molecules adsorbed on the transition cluster, the trends change very drastic when you change the molecules adsorbed. Basically, we capture several features that are important, and several difference between when you have for instance, for instance, a CH2 adsorbed or a CH2 adsorbed with more two hydrogens co-adsorbed. We have noticed some difference and so on, but it's not was not like this that we have the amount of data in this case was enough to make the trends clear. In this case, the quantity of systems and the way that they are spread was not enough. So there is a limitation of the method of the framework, that is, you need to have data, basically. To do that, to employ this kind of framework, I developed a code in a package in Python that basically do the hard work for you. You can, for instance, give a folder for it. It finds your calculations. It extracts the informations, do molecular analysis such as effective coordination number, distance, average, find the atoms in the surface, and so on. And now to do the featurization process. For instance, it divides your data in several classes, mixed classes, do several of the filterization process that I addressed in the beginning of my presentation. And also it plots for you. You can save the data and plot elsewhere, or do, for instance, a machine learning approach with the data, and so on. And it operates recursively, so it does not matter if you have 10 calculations or 10,000. It runs in the same way. In conclusion, I have developed this framework. It's very easy to employ. This work was published in the beginning of this year, and this one is submitted for the full journal. I have developed this framework. It's very easy to employ. It's basically Python. Quantitative, it can measure quantitatively the trends, which you cannot do it visually. Handle each data manually. You can apply it to any material, so there is no material limitation. It's very little explored. The reviews appreciate this kind of new approach, new analysis, the referees. I have contributed to 3 works. The 2 of them are published. The other one was submitted. And also the implementation. In the perspective, I should address in another article the methodology in more details, and release the Quandarium package. I would like also to acknowledgement to the agencies and institutions, and thank you for your attention.
Anyone? Anyone?
So thank you for the very nice talk. And you said that your package is able to actually get data from directly from the outputs of the programs. So currently, which software packages are you supporting? Like FHI, VASP, what else? And how hard it is to implement a new parser, let's say, to get data from different programs?
Okay, I don't have the code here. But basically, when you have your calculations, there is a package ASE, atomistic simulation environment in Python, that can read like a lot of outputs structure. So my idea was basically you can employ it, and you will have most of the times only the energy and the final structure. However, you can use some implementation. I do my implementation for VASP and FCHIMES. In my case, I extract a large amount of data. For instance, I extract this, data from charge per angular moment of each atom. So these guys here, the way you structure your information will define how much information we will have. So my implementation structured a lot because I build up just for it. But if you employ, like for instance, in other codes, not VASP, not FGIMES, the implementation is some limited. I built a function to extract data from one calculation, and a function that take this function and operate recursively. So what you need to do is a function that extracts data from one calculation, and it operates recursively and so on.
I think, thank you for the nice talk. You mentioned concern the discussion on the data. For example, you show the diagrams there. But for example, can you show one of them? For this one, for example. Once you have this analysis of the data, then you have the diagrams, then you have the slope of the curves, but without, do you think, for example, without the chemistry insights, could we identify all the important properties as we could identify looking the quantum, based the chemistry inside, for example. This one identify was the most important variables, but it just correlate the energy with a particular variable, but not all the variables together. It's possible to analyze all the variables versus all the variables together. I mean, all the properties versus all the properties.
Okay. First thing you need to consider is about the, for instance, here, I divided the data in classes. So, for instance, I don't look to the two compositions together. If you put them together and don't look for it, you will find nothing with this correlation in this approach here. But in principle, you can create something to look for some kind of separation in the data and then address exactly this automatically. So it's possible. Yes, yes, yes. Because the correlations are easy to calculate. The result is meaningful here because when we calculate this correlation, we use our insights to divide the class. If you use some approach to divide it, to search for a way to divide it and employ the correlations and get high correlations, you will find, and it will work. For instance, this guy here, basically what I did was search for somehow divide the cluster, divide the data, and clusterize the correlations. Then I find two different structures. One for the guys that have a pattern, and one for the guys that have the other pattern. So if I go further, I probably will find something like the split between the composition.
Okay, so let's thank Johnatan again. Oh, and just let's thank everyone that, like all the speakers again, one last time.
Okay, thank you very much. Okay, I think that we have today up to now 15 talks. I think all of them was, I think, great talks. And then was, I think, all of them address what they are doing on their projects, okay? And then provide what they have obtained up to the moment. I think it's very important. I think what I remember the project is concerned not in the right order because we have to exchange the orders, okay? But in the morning, we start with the P19, the batteries. I think we are moving, okay? And also we are moving what we're proposing. We are looking for new patterns of the sodium batteries, which is important for the project too. And then we move to the project 17, okay, about CO2. I think we are moving quite well, and then moving this direction of the reaction, also the storage too. Then we come to the project 18, okay. I think with the chalcogenides and also with the perovskites, we are, I think that's important for the perovskite because we have experimental result that's going on. It's important to get closer. And the chalcogenides is important to find a path how to reach closer that way too. And also we come with this what is pretty future work too. And then I think then we come up to the project 16. I think this methane conversion, we have the concern the using the nanoclusters. We have made some progress, and the zeolite teams are working. We are making tight the things. I think it's quite very important. And then we come to the project number 20. I think the machine learning is a good example. One part and the important here is the full, for example. Maybe we have to ask the full. Do you have enough computational resources to generate like with 200,000 K molecules, 200,000 molecules, or hundreds of thousands of systems. Maybe this question have to be answered later, but maybe we will not have. But the question is the following. Those works that you are doing that show, like Marco Kill showed, that's in collaboration with my team, or Jonathan shows today, we should try to explore and to combine the expertise, machine learning, the way that you can, if you can try to get machine learning techniques or any computational techniques that you are able to move what you are doing quantum chemistry up, it's a plus for us. And then, as Marcus Kill mentioned at the end, okay, there are several possibilities, a wide range of possibilities. We can explore them in different approaches. Okay, the approach that you are using, for what I see at the moment, is not going to be successful to do the machine learning quantum chemistry without a quantum chemistry sit behind together side by side. Today, after 18 months, we can say it is not going to be possible. I think Ronaldo agreed with me with that. Marx agreed with me with that. Without the quantum chemistry, one chair and the computational scientist, another chair, the thing will not move. Okay, but however, there's a lot of possibilities. We have to explore them together. I think because the project number 2 it works as a horizontal project inside of the 5 projects we have. I mean, there's a lot of potential how you can combine them. But it's very important that we set up the right goals and to have the right people that can sit together side by side to combine the expertise. Without this combination, my opinion, after 18 months of working together with Marcos, then also Ronaldo traveling there, Jonathan went there a few times, I went there too, they come here too, it will be very challenging, okay? Because the gap is huge, okay? And at the same time, there's a lot of room for improvements. As the question that I make, for example, concern the project number 19, concern the problem about the force field developments. For example, I think inside of lumps, Luis mentioned, there's already potential that comes from machine learning. I think there's lumps that already potential inside, not lumps or lumps, there's a lot of potential that's come from there. Recently, this was a paper from CRES, just this week, not fully available. I think it's available the abstract, but not the PDF yet. Means a machine learning development to predict thermodynamic properties of materials only based on the endpoints of the material properties. Okay, means from what I know from CRES, when the people was doing GW calculations for many years, only few groups has a technique. Only few groups could do GW calculations. In 3 years, CRES put everything from GW inside VASP and make it available for the full world. The same is going to happen in machine learning. I'm pretty sure. CRES is going to make a lot of development in machine learning, combine it inside VASP and make it available wide world. Okay? Means this is going to happen. Because all the paper that is coming from his group is in this direction. Which means that for in the future, we're going to be able to perform VASP calculations and to combine them and machine learn at the same run. Most probably. This is going to happen because he's doing several papers on this line. And from what I know from his development, his groups, these things come aligned with that. And then we have to make the questions concern, for example, how we should combine the expertise of machine learning inside of the project is come from 16 to 8 to 19, and how to get this approach and how to make this technique more useful and how to get our works that, for example, of those works those tests that combined that Jonathan did together with Priscilla, Carlo, with Chris, with Marcos Kilis, with Ronaldo too, that we published, that was published in few magazines, all the referees mentioned, okay, very good that was there. Oh, very important, very nice insight, comes from independent analysis. Means looks simple. Yes, looks simple. But it's something that if you are the first one that you are doing and put there, it means makes a difference. Okay, and this is what counts at the end. Okay, you have to make innovations and to go up. This is very important. Okay. Okay, now you're going to have the poster sections. As I mentioned before at the beginning of today morning, we have this prize for the posters. They are separated in postdocs, PhD students, master students, and scientific initiation. It's true, it's not so much money. It's 200 reais for each one, who is the first one. Okay, everyone is going to select that. And you're going to have the prize for the best talks divided in postdocs and graduate students. Okay. Unfortunately, the faculty members are outside of this prize. Okay, Ronaldo, okay, Marcos, because Mateus, because you are different level. Okay, We have to put the competition at the normal way, okay? But then those talks you're going to have to vote there to select who is you think that provides the best, deliver the best talks, and then so on. And tomorrow morning we start with the hands-on. The hands-on will be conducted and delivered by Ronaldo, Marcos Quiles, and also Jonathan, and also Gabriel. Two of them, Gabriel, will be there. I think Guilherme, Felipe will be there too, no, Felipe? Supporting team too, also sure. And then they're going to conduct it. We're going to have 2 rooms, okay, because the number of participants is a bit large. You're going to have 2 rooms, and you're going to have an online transmission from one room to another, okay, because they also prepare several tutorials, and then they are maybe we discuss with them. The tutorials are very good. You provide an initial pathway for so everyone that wants to start with the Python and go beyond of that. The blocks are very good. Many things that they show here, they're going to do there with you, I think. And then on Friday at 4 p.m., we're going to close the workshop here, okay? And then you have a final coffee break here, okay? And then any question that you have, Jacqueline will be outside, or you can send an email for her. I think that her email is the most common one among us. I think is very important. Someone have some question, just be free to open to answer it. If it's not the case, we'll just go for the coffee break in the poster. Okay, thanks a lot.
Oi? Então, eu acho que ele travou em uma